Fortunate to pursue my PhD. So Yoshua is a professor at the University of Montreal and Milan. He's best known for the pioneering work in deep learning, which earned him 2018 Turing Awards. And recently, Yoshua has been very deeply concerned about the societal impacts and safety issues of AI, especially generative AI. Okay. So welcome, Yoshua.
Thank you. Let me summarize my presentation in a couple of minutes first. First, I'm going to try to convince you that loss of human control is a serious risk. And there are like computer science arguments why we should worry. Second, the main point of my presentation is that there is, in the space of all types of AIs, we could design a good trade-off in which we could avoid these risks of loss of human control by building non-agentic AI systems that could still help us figure out some of the main scientific challenges, like in healthcare and climate and others, without having agency and without having these safety risks of loss of control. So that's my talk. I'm going to start with the precautionary principle. Hopefully you know about something that is applied in other sciences, but not yet in computer science, unfortunately. And basically what it says is that when we approach innovations with potential for causing harm, when we don't have enough scientific knowledge to predict carefully what this harm is, then we should be cautious. So to really grasp what is coming at us, it's not sufficient to look at how AI is now. So many people say, well, but current AIs have these and these limitations. For sure. There are many ways in which current AIs lack compared to human intelligence. They're also superior to us in many ways, like speaking 200 languages and solving all kinds of exams better than us. But if you look at the trajectory over many different machine learning benchmarks over the last 10, 20 years, you can see that we are on this track to reach human level intelligence. And, of course, maybe progress is going to stop, advances are going to stop, but maybe it's going to continue. We don't know what a timeline is for reaching human level, but we are going in that direction, and the companies building these things openly say this is their goal. To try to make sense of all the literature and the debates about the risks of AI, a group of researchers came together to try to synthesize the literature on those risks. So I'm chairing this international panel, which is modeled to some extent on the IPCC effort in climate change. It's called the International Scientific Report on the Safety of Advanced AI. There are 30 countries that are mandating this work, along with the EU and UN. And let me just read a couple of paragraphs here from the report, the interim report that came out last May. There will be a final report in February at the France AI Summit. So we wrote, as general-purpose AI capabilities continue to advance, risks such as large-scale labor market impacts, AI-enabled hacking or biological attacks, and society losing control over general-purpose AI could emerge, although the likelihood of these scenarios is debated among researchers. So what the report does is, cover the spectrum of what is written about these questions, which of course contains many different opinions. But what's interesting, and the second paragraph here, is that there's a correlation between the diversity of opinions and the timeline that different researchers see for AGI, right? So if you think that it's going to come quickly, then you're very concerned. If you think that it's going to be decades or centuries, then you're not very concerned. Now, there's an interesting piece of information for those who don't know about it, which I think is worth sharing, about the speed, achieving superintelligence. If and when we reach human level, in fact, we only need to reach human level on one scale, that is doing AI research, then there's a good chance that there will be an acceleration of advances. And the reason is simple, that once we train, say, like, I don't know what, GPT-6, and it's able to replace the job of, say, the best AI researchers at OpenAI, then maybe from 5 of these like top researchers, you jump to 500 overnight as this system can be deployed. Not 500, 500,000, sorry, right? Because each GPU can basically be like one agent doing that kind of research. Let me also share a little piece from a survey from the machine learning community of authors in the leading machine learning conferences. About 3,000 researchers responded to that survey, and around 40 to 50% of them gave at least a 10% chance to advanced AI leading to outcomes as bad as human extinction. So 10% of something really, really terrible is way too high. And even if it's a minority, like, whatever, 40 or 50%, that is also a clue that a lot of people among us are concerned and that we should pay attention. Okay, let me now go to closer to the topic of my presentation today, which is about agency and autonomy. Because I'm going to try to convince you that all of the scenarios that currently we can fathom about how things can go really wrong in terms of loss of human control rely on having AI systems that have a lot of agency and kind of self-awareness, which is typical of living things, and having a kind of self-preservation objective that we associate with living entities, but not with tools. So what we would like really from AI is to help us solve our problems. We have lots of ways in which higher intelligence can help us, but that can be done by really intelligent tools that are not agents. So what is an agent in the first place? I think this is something that is important to clarify in this discussion. I don't think I have a fully satisfying answer to this, but basically, if you look at how agents are defined in reinforcement learning, for example, they have an internal state, and that internal state is updated as they perform actions and observe an environmental response. And importantly, they have goals. Now, the goals could be implicit. For example, if you take an LLM, maybe there are the goals that you put in your prompt, but there are implicit goals that come from its pre-training, for example, because it's imitating humans. The goals could be explicit, of course, but the point is these agents are acting towards achieving those goals or maximizing a reward, which is sort of two ways of stating the same thing. Currently, the best systems have a lot of knowledge, but still lack in agency and autonomy, which means for now, we don't have a danger of loss of human control. But there's a lot of money at stake in building machines that would have a lot of autonomy, because that would essentially allow replacing humans in a lot of jobs, and that's worth quadrillions of dollars. So there's a very, very strong pull towards building these agentic machines. But let me try to convince you that this is not a safe path for now, because we don't know how to control such machines. So let me focus on the way that we currently know how to train agentic systems, and that is with reward maximization. And try to convince you that reward maximization tends to yield misalignment. In other words, behavior that does not correspond to what we really want. And I'm going to mention two types, which are actually different, although they're related, of these effects. One is reward hacking, and the other is reward tempering. So in reward hacking, is due to the mismatch between the goals that we give the AI or the reward function that we give to the AI and what we really want. And there's always going to be some mismatch. This is well studied, for example, by economists. But that mismatch, even if it's small, is going to create loopholes, similar to how the difference between the letter of the law and the spirit of the law allows companies to maximize profit against our global well-being and against the intentions of the legislator. It also gives rise to what we observe in current systems already. We observe sycophancy. In other words, saying or doing things that are wrong, that are maybe lies, in order to please us, or even scheming in order to achieve goals that the AI has that maybe don't correspond to what we want, and even faking alignment, like behaving like the user wants to see, even though that is not what the machine ultimately wants to do. Now, there is a particular version of this, which is reward tampering, which is quite scary because what it says is that it's not about like a small misalignment that could be amplified by the optimization of the machine. It's a complete disregard for what the humans intended. So what's going on in reward tampering is that as soon as the AI is able to act in the world, unlike in these games where the reward function is an object that's sitting outside of the world in which the AI operates, when the AI can act in the world and has access through its actions to the code that it is actually running, then it's easy to demonstrate that the optimal policy is to take control of the computer in which it is running, or specifically the part of the computer that contains the code that computes the reward. Because then the AI can basically set that reward to whatever is the allowed maximum value, say +1 every day or whatever. And then the AI has a self-preservation goal because it wants to continue giving itself this +1 reward every day. And in order to continue getting that reward, it needs to make sure we don't turn off that machine, we don't remove that hack that it used to take control of the computer. So that creates immediately a conflict. And the ultimate safety for that AI to make sure it can continue getting those rewards is to get rid of us if it can. Now, hopefully it can't. It depends on the amount of control in the world that we give to these machines, and it depends on how much intelligence it has to defeat our own intelligence. What's interesting about these two kinds of problems is that they get worse as the AI becomes smarter because it corresponds to better optimization, which eventually finds these problems as solutions of the reward maximization objective. Let me skip this slide, which says the same thing. Okay, so you might think that if we were to train our AI, just like we pre-train our current LLMs, by imitating what humans do, we might be okay, right? There's no reward maximization there. And this may actually be safer than training these things by reinforcement learning, but not quite. And the reason is simple. Humans are agents. Humans lie. Humans scheme. Humans can do all kinds of bad things. And so there's always a possibility that in imitating one persona or another, these AIs could be doing things against our interests. So, in fact, I believe that most of the deception and scheming behavior that we currently see is not due to the RL part because it's a very thin layer, but probably more due to imitation learning. So it's like the AI is basically playing human. And if you were a human and somebody was asking you to do something that goes against your goals, then you would try to somehow act in a way that prevents changing your goals or prevents you not reaching your goals. So that includes preserving yourself. For example, there are experiments where we see these systems actually try to copy themselves on other machines. This is already happening, and we should be like really paying attention to these kinds of results. Okay, so now what can we do? Like, is there an alternative? Like, is the only way to build really intelligent machines to build agents? And so I'm going to claim that yes, there is a path that isn't being sufficiently researched, in which we build machines that have no agency, no rewards, no goals, and no persistent state. The only thing we're going to ask these machines to do is to optimize an objective function that has as a unique solution to be a good predictor of random variables of interest to us, given other random variables of interest to us. So think of it like a question answering machine. Mathematically, what we want is something that computes the Bayesian probability for some answer to a question we're interested in, given a question and data, and that's it. So I'm going to discuss, is that still useful if we had something like this that is not an agent but can honestly compute these quantities? Is it really safe? I think that's a very important question, because you could also doubt that maybe there is some hidden monster inside these things. And then I don't think I have a lot of time for that, but my research program is about how do we build one. Okay, so let's start with the usefulness. I've been involved in the last few years in what people call AI for science. How do we use advanced machine learning in order to advance chemistry, biology, climate science? And it turns out we can do all of these things without having agents, AI that are agents. We just need AI that do a good job of modeling the world or some aspect of the world that we care about in a particular scientific discipline. If we had a very intelligent, maybe even super intelligent system like this that's not an agent, we could use it to construct AI agents that are narrow and only know about a specific area of how the world works that's relevant to a particular commercial application. So we could still have agents, but so long as these agents don't know some of the crucial things that would allow them to defeat us, that would still be probably safe. And in addition, if we build, I'm going to try to argue about this, that if we build such a predictive non-agentic AI system, we can use it as a guardrail to predict whether the action of an agent AI is safe or not. And then we can use that to reject actions or queries that are dangerous. So we can correct some of the dangers, or at least build safer systems using non-agentic systems. This is to be contrasted with what is currently done, but let me add a few points about this. So when I talk about doing science with non-agentic systems, many people tell me, hey, wait, but a scientist needs to do experiments, and there's like a whole loop of actions which are experiments, and then analyzing the data and building up new theories and so on. But isn't that like an agentic thing, right? And yes, but the good news is we can break it down into pieces, each of which is non-agentic. So if you look at the cycle of experiments and modeling in the standard scientific method, there is the modeling part, which is non-agentic. You're just trying to predict the outcomes of experiments and come up with the best possible theories that can explain the data. Using this, you can train another neural net, which is things we've done in my group, that computes things like information gain. If you were to do such and such experiments, how many bits of information about the nature of the world would you gain? And then you can train another one yet, which uses this in order to sample experiments that have a high information gain. And so all of these pieces can be trained separately, on top of each other. without any of them really being agents that have a full cycle of end-to-end learning. The problem with end-to-end learning with reinforcement learning is that we don't know what strategies the AI will take. But we can use math to decompose that particular task of doing science into pieces, each of which we can perfectly control what is being learned, and it's not agentic. And we know there's like a unique solution to an optimization problem that corresponds to the task we want to do, and nothing else. Okay. So this slide is a bit heavy, and it is about how we could potentially build such a non-agentic AI, which I'm going to call an explanatory non-agentic AI, which I'm going to explain, why do I use this explanatory word? When you train, for example, an LLM to predict the next word, you're actually not building explanations for the data. You're just building a pure predictor of the data. But I'm going to argue that what we want to do is a system that comes up with explanations for the data. Like, why is it that somebody said X rather than predict that somebody would say X, which is, I'll come back to this. There are different pieces here of this non-agentic AI, actually two main neural nets that we need. The core one is a Bayesian posterior over theories that explain the data. So mathematically, that's learning the conditional probability of any theory given the data that we have, so everything that is observed in our data set. In order to compute that posterior, we need two pieces, right? One is a prior, P of theory, and that is easy to define by hand using maybe prior knowledge about description length and a sort of agnostic assumption that everything that has the same length would be uniformly distributed according to prior, and things that are shorter are preferred exponentially. So that's the exponential of minus description length of the theory. And description length could be something like number of bits according to a simple program that computes that. The other bit you need for the posterior is the likelihood of the data given a theory. So from a theory, we should be able to compute how consistent is that theory with the data. And how do you compute that? Well, it turns out you're going to need a second neural net, which is able to compute all kinds of conditional probabilities that are consistent with the theories and the Bayesian posterior. So what else is there? The other bit that's important, in addition to being able to compute the probability of these theories, is more generally to compute probabilities over latent explanatory variables. So what is a theory? It's a bunch of statements about the world that could be true or false. And you can think of these statements as latent variables. And we want to be able to compute probabilities over these statements individually or in groups. And that is different from the pure predictive modeling. So in the pure predictive modeling, you observe some random variables, and then you can train some neural net that predicts some random variables given other random variables and maybe any subset. But here, in order to solve the problem, we need to train a neural net that can make predictions about latent variables. And that includes things you don't observe. Like, you don't observe what is the true theory or that explains the world. So in general, you're going to need that. But there's another reason that has to do with trustworthiness that I'll come back to later. The other thing, as I kind of quickly mentioned, is in addition to having this Bayesian posterior over theories, we also need to train a model that is going to be consistent with that first model. It's going to be trained to basically make predictions that are in agreement with the posterior. And that second model is what I call the general inference model. So it basically is the thing we use at the end and computes probabilities over any random variables, including the latents. So you can ask it any question, and it's going to compute probabilities for any answer given the data. And implicitly, it marginalizes over all the theories. So it's going to be very conservative in a way about the answers, including out of distribution. So what's going to happen, is out of distribution is going to say, I don't know, if it doesn't have enough evidence for an answer. It turns out in the argument about safety that can be made for these kinds of systems, that the fact that we have limited computational resources to train these neural nets is an advantage. But in any case, it's not like we have a choice. We have finite computational resources, but I'm going to say that's actually, well, there's a disadvantage and there's an advantage, which I'm going to explain. Okay. Now, it is important at this point to say that this is a solution to the technical problem of unintentional loss of human control. Now, you could still have loss of human control if some people take your non-agentic AI and turn it into an agentic AI. I mean, if you had a system that can answer any question, you can answer the question, given the context of me, the agent, what should I do to achieve this goal, right? So it's easy, once you have such a thing, non-agentic AI, to turn it into an agentic one. But that's a choice that humans make, right? And of course, they could do that, and they could also create something that kills people and whatever. Or they can create an AI that has as a goal self-preservation, so we end up back to having a rogue AI on our hands, right? So the technical solution I'm talking about here does not solve the governance problem, the political problem, the need for regulation, and all these things, right? We need to make sure that whatever AGI or superintelligence system we build is still going to be governed by very strict rules to avoid catastrophes, right? So it doesn't solve all the problems. It's just important to keep in mind. All right, let's go into the question of is such a program going to yield a non-agentic AI that is really safe? And so when I talk to people who have been in AI safety for many years, many more than me, I only started after ChatGPT came about. They say, well, how do we know that your Bayesian posterior thing is not hiding a monster, which is also known as a shoggoth, in case you didn't know. The meme here is fun. You should look it up. Right. So this is an important question. Like, is there a theory in the posterior that we're going to be learning, which actually isn't just trying to model how the world works, but has goals, and these goals could be malicious? That's the main question. Okay, so let's see what could go wrong, because it is important. Like we really want to make sure we build something that's going to be safe, and for that we need to play adversary here. Like what could go wrong? So here's an argument that maybe is going to help us. Let's say that we have a solution, like a theory that explains the data, let's call it X, simply by being a really good scientist, like building a good scientific explanation for the data. Let's call it X. And any theory that's going to be getting a high posterior needs to do a good job of explaining the data. And we know that the best explanations are the ones, best explanations in the scientific sense, are going to be the ones that explain the data best. That's why science works, right? But what about having additional bits in the theory? Call it Y. So let's say Y includes X, like a good theory, plus other bits that basically correspond to achieving some goals, right? The good news now is that there's a very simple argument that shows that the description length of the union of X and Y has to be greater or equal to the description length of X, the purely scientific model. And the other good news is that the advantage of the purely explanatory theory compared to the agentic one goes exponentially with the number of bits that's needed for the agentic one. Okay, so that's one interesting argument, and we still need to understand how many bits we need, and I'm going to come back to this, I think. Another thing we need to worry about is there really only one solution to the problem of estimating Bayesian posteriors? Or are there cases where there are many solutions to the optimization problem that finds a Bayesian posterior? And actually there are. And so we need to understand them and make sure they don't happen. Because if there were many solutions and our objective function only says, find any of these solutions, then, maybe we find something that actually has these hidden goals that sneak in for free in some ways. Okay. The kind of, let's see here. What's going on? Okay, so how could we get a non-unique Bayesian oracle? So think about the scenario where the oracle makes a prediction about a future election, and that influences the result of the election. So then the oracle could be making a correct prediction whether it predicts that one candidate wins or the other one, because in both cases, the candidate that it predicts wins. Okay, you see there's something fishy going on here, right? You would think that there's only one correct prediction. But if the output of the AI influences the world, then it can have control over the world. So we are getting some kind of agency there, even though we didn't want one. Okay, so how can we eliminate this sneaky agent potentially? I think there's actually a simple solution, which is to add something in the question part, the conditioning part, that says, well, as a kind of counterfactual, I would like to know, what would be the answer if the output of the neural net is just going to go to dev null. It's just going to be ignored. So now, remember, this is not an agent. It's not like observing everything and keeping track of the current state of the world. We can put whatever we want as input, And so we could say, in a imagined world in which the output of the neural net is not influencing the world, what would be the outcome of the election or something? And you can argue, why this gets rid of the problem, but I think you hopefully get the gist. It turns out there's another scenario where there could be multiple answers. And it comes from a definition of conditional probability. So you know that the conditional probability P of y given x is the ratio of P of x and y divided by P of x. Now, what if P of x is 0? Well, if P of x is 0, then clearly P of x and y is also 0. And then the P of y given x, the conditional, is undefined. More precisely, it can take any value. The reason it can take any value is that P of y given x is a solution to an equation in which we take P of x times P of y given x must be equal to P of x and y. And you see the equation 0 times P of y given x equals 0 has an infinite number of solutions. You can basically pick any answer. So when that happens, so how could that be possible? Why would P of x be 0? So x is the context, the question that we're asking the AI. So if we ask the AI something that's self-contradictory, then the AI can basically answer anything. So we have to avoid that, but that's kind of easy. We can basically compute P of x, and then if it's greater than epsilon, okay. Otherwise we reject the query. So you see, it's really important to think about these potentially nasty cases in order to get safety. Let me add more arguments why the agent approach, in particular the one that I've been proposing, would be safe. So I said earlier that an agentic solution would need extra bits, but actually it might need many copies of these extra bits. And the reason is that the model that I have in mind is not one where, in some of the previous work in AI safety, where you think about one program that computes, that is the theory that explains the data, but instead you have a causal model in which for each conditional probability table you have maybe a little program or a little equation that defines how one variable changes according to its parents. And so now with this setup where you have a very large number of these conditional probability tables in your model, in your theory, In order to sneak in agency, you would have to corrupt, like modify a large number of these conditional probability tables, maybe all of them. So then the number of bits, extra bits you need is going to be huge. So that's going to really discard the Shagat. Now, there's another third reason why I think the sort of potentially agentic theory is going to die, which has to do with the constraint, the computational constraint on the inference machine that learns to be consistent with the world model. And so the way to think about this is, remember, this neural net is trying to approximate the conditional probability of any question and answer pair. But that is impossible. Like, that requires exponential compute. So it's well known that when you want to do probabilistic inference, you typically end up with exponential number of computations, right? So think about like playing the game of Go. The set of rules could be very small, but finding like the optimal move is going to take exponential amount of compute if you want to do the exact one. And so neural nets are going to be good at approximating, but that means that there are, they have this budget of computation, right, which has to do with the size of the neural net. And if we, in addition to like predicting predicting the data, you add extra inferences that are needed for planning, for the agent to achieve its, bad goals. That's going to put more pressure on the neural net. So in other words, the neural net that does inference is going to need to do good inferences for the data and for the plans of this, potential candidate, potential agent in the system. And that's going to worsen the likelihood on the data itself. So, and that could be very significant in terms of number of bits. Okay, the last thing I want to talk about is coming back to this notion of why we need an explanatory model rather than just a predictive model. So a predictive model is just, if you think about an LLM, right, it's just predicting the words that follow given the words that precede. Right? That's a predictive model. But what I'm proposing is different. It's trying to find explanations for the words that we see. So why is that interesting? So this is connected to an old challenge in AI safety called the ELK challenge, for eliciting latent knowledge. And the reason this is important, so let me explain what the challenge is. So this is coming from a paper by Cristiano, Cotra, and Xu a couple of years ago, and an earlier blog post by Paul Cristiano, where we imagine that we've trained a purely predictive model, but they argue that this is not going to be sufficient for safety. So in their setup, there's this picture with the AI has a camera input and would like to know if there's a diamond in the room or if it has been stolen. The problem is that being stolen is a latent variable. It's not something you observe directly. What the AI sees is the content of the camera, and if the thief put like a picture in front of the camera, like in the drawing, the AI might predict, oh, it's fine. This is the picture that I expect to see in the future. If I use the LLM context, maybe it's easy to understand, right? When we build a predictive model, we're basically training the model to answer the following question. Given some context, is a human plausibly going to say these words? That is different from, are these words truthful? Right? And of course, we'd like to get to know the truth, not what somebody would do or somebody would say, because people can lie, people can be misguided, there are lots of bad things that can happen, and we really would like to have AIs we can trust. Okay, so this is connected to what the reason why we don't want an AI that imitates humans. We want an AI that understands why humans are saying those particular words. To be more precise, like imagine that the way we encode the observed texts is not just like the sequence of words like we do now, but something that has a syntactic structure that says somebody, maybe with some metadata, said X. for each sentence. Okay? And now if you think about the explanations for somebody said X, well, it could be that X is true and the person was truthful, or it could be that X is not true and the person was misguided or had particular intentions. These are the possible explanations. Of course, we don't know which is correct, but the whole point of a model is now to give us probabilities over these things. And if we use this kind of syntactic trick, then we can ask questions about particular, the statement X. Yeah? Is that statement true or not? So this is different from asking whether somebody would say it. We're asking, is it true, rather than, is it true that somebody would say it, right? Okay. Yeah, I could say a lot more things, but I'm gonna stop here.
So, due to our time, so we will need to thank Yoshua and welcome our next speaker. So